Hi everyone, myself and Arun Kumar from SNS College of Technology in the Department of EC. In this video, we are going to see about translational and rotational mechanical systems. The differential equations modeling of mechanical systems. There are two types of mechanical system based on the type of motions. First one is translational mechanical system. Second one is rotational mechanical systems. The translational mechanical systems are based on mass, spring, dashpot or damper. Because the translational mechanical systems are based on the movement, it is along with a straight line. So this has to be followed by the following basic components: mass, spring, and dashpot. If a force is applied to a translational mechanical system, then it is opposed by opposing forces due to mass, elasticity, and friction of the system. Because if you are choosing your spring as an example, then automatically it is having the following functions to be calculated. First one is forces and concern mass and as well as the elasticity and frictions. Since the applied force and the opposing force are in opposite direction, the algebraic sum of the force acting on the system is zero. Let us now see the force opposed by these three elements individually. Mass. While forcing a mass in the moving coil or element, it is based on the opposing force due to the mass. The opposing force is proportional to the acceleration of the body. Assume that elasticity and friction are negligible, then the following ways to be calculated. So here F is force and A is equal to acceleration force and acceleration force. So the F is proportional to acceleration, and the equation can be calculated by F equal to M of Fm equal to M into d square x by dt square. So F is the applied force and Fm is the force due to the mass, M is the mass, A is the acceleration, and x is the displacement and spring. So if you are applying your spring and movement may be changed based on your vibration and accelerations. So like that calculations can be followed by force directly proportional to x. So here F is applied force and Fk is opposing force due to the elasticity of the spring. K is the spring constant, x is displacement. So Fk equal to k into x. So final equation of Fk equal to, because of force you are giving, so Fk equal to k into x. K is the spring constant. K is the spring constant. X is the displacement. Because if you are giving more force to the spring, then automatically based on the acceleration, it just move towards the other end with the vibrations. And next one is dashpot. The movement of the particular or object can be calculated by using this dashpot. So the dashpot Fb directly proportional to velocity. So here the Fb is opposing force due to the friction of the dashpot. P is the frictional coefficient and V is the velocity and x is the displacement. So Fb directly proportional to V can be calculated by F equal to Fb equal to B into dx by dt, because you are placing the displacement of the object so that we can choose as dx with respect to time. So B is the frictional coefficient. So after calculating all the three parameters, we can able to find out the mechanical systems. The rotational mechanical systems about a fixed axis, it is also a three basic elements: the moment of inertia, torsional spring, and dashpot. It has to be calculated by the after the next slides. The moment of inertia. In a translational mechanical systems, mass stores kinetic energy. Similarly, in rotational mechanical system, moment of inertia stores kinetic energy. So the kinetic energies are based on the moment of the force which is applied to the object, as well as the moment of inertia, as well as the angular changes and the angular displacement. Because if you are moving your object, means then automatically your angle has been changed and the corresponding the moment also change. This has to be calculated in this moment of inertia. Next one is torsional spring. The translational mechanical system, the spring stores the potential energy. Similarly, the rotational mechanical system, torsional spring stores potential energy. If a torque is applied to the torsional spring, then it is opposed by an opposing torque due to the elasticity of the torsional spring. This opposing torque is proportional to the angular displacement of the torsional spring. Assume that the moment of inertia and frictions are negligible because it is only choosing the angular displacement operations. Torsional spring. The moment of the value is calculated by using this torsional spring by Tk, the T1 equal to Tk because the how the opposing torque due to the electricity of a torsional spring, and K is the torsional spring constant, and theta is the angular displacement. So how much distance has been transferring the elements with the help of this torsional spring constant. It has to be calculated. And as part is the movement of the rotational frictions. It is calculated based on the rotational of the coefficient and the angular velocity and angular displacements t and theta. The final equation here v into d theta by dt. The corner frequency in the board plot is based on which factor is going to define the corner frequency. First one is frequency at which the Bode plot slope is 0, the frequency at which the Bode plot slope is -10, the frequency at which the two asymptotes intersect, the frequency at which the two asymptotes meet. The answer is the frequency at which two asymptotes meet, because the frequency at which the two asymptotes in the Bode plot meet is termed as corner frequency because it's a lower frequency as well as the angular frequency. At the time we have to calculate the corresponding equation. So hence the correct answer is option D, the frequency at which the two asymptotes meet. Thank you.